OpenStax textbook, Calculus Volume 2. We are working with trig substitution in section 3.3. We just finished working with problems of the type square root of a squared minus x squared. Now we're moving to square root of a squared plus x squared. So in these, whereas before it was convenient to use the Pythagorean identity sine squared plus cosine squared equals 1, this one is going to use the secant and tangent identity. So that one would be, let me think for sine squared plus cosine squared would be over cosine. Tan squared plus 1 equals secant squared theta, or x, sorry. However, let's do theta because that's what's going to go in the problem, usually. All right, so when I have a problem with a square root of a squared plus x squared that I've already determined it's not convenient to use another method, then I will replace my x with a tan theta and my dx with a secant squared theta d theta. It will end up giving me the square root of a squared secant squared, which is a secant theta. Okay, we already know this. We're going to jump through after we do this a time or two. Simplify the expression, evaluate, and then we are going to use our reference triangle again to fill in information. Now, we'll say there are problems in the book that use more than one method to solve things, and I have chosen what I thought was the simpler of two methods to help you out. I will also point out that the reference triangle for this one, since we're using x equals a tan theta, then x over a would be my tan. So that would be opposite over adjacent, which makes the hypotenuse a squared plus x squared. Okay? Hush. All right, so let's look at our first example. We have the integral of dx over square root of 1 plus x squared. My x is going to be 1 tan theta. My dx is going to be secant squared theta d theta. So we're going to have the integral of secant squared theta d theta over square root 1 plus tan squared theta. Now, 1 plus tan squared is secant squared. When we take the square root, it's just secant theta. So we have the integral of secant squared theta d theta over secant theta, which means integral of secant theta d theta. We used this in the previous section, and the integral is the natural log of secant theta plus tan theta. Nice dog. Plus c. If we use our triangle, where we have x here, 1 here, and square root of 1 plus x squared here, then our secant theta is hypotenuse over adjacent, square root of 1 plus x squared. Our tan theta is x over 1 plus c. They kind of set us up with a nice easy one to start. I feel like they kind of just lobbed that one at us. Okay? Next one. Using a different substitution. I don't love different substitutions. I like the substitution we already used. But I am going to show you this one just because they do have it here. Obviously a reason for it. So they want us to specifically use x equals hyperbolic sine of theta. So if x is sine h theta, dx is cosine h theta d theta. So we have the integral of cosine h theta d theta over square root 1 plus sine squared h theta, or sine h squared. Never write that one right. Let's try again. All right, which this does fit the Pythagorean identity for hyperbolics, which is 1 plus sine h squared is cosine h squared. So we have the integral of cosine h theta over square root cosine squared, no, cosine h squared theta d theta, which is the integral of cosine h theta over cosine h theta d theta, which is the integral of 1 d theta. So from there, the integral of 1 d theta is theta plus c. Our theta in this case, if we took the inverse here, is inverse hyperbolic sine of x plus c. So this is an equivalent answer to what we had before. All right, let's use our information for good to find an arc length. Find the length of the curve y equals x squared over the interval from 0 to 1/2. All right, so y is x squared, dy dx equals 2x. Our interval is from 0 to 1/2. So the arc length is going to be, let's remember what the arc length formula was. So our arc length formula I've put here, dy dx is our f prime of x. That's what's going to go here. So we have the integral from 0 to 1/2, square root 1 plus, if I plug in a 2x there and square it, I have 4x squared dx. So my a is 1, but then I have the 4x squared. So what do we do with that to make this work? So we're going to throw some strategies in here that you're really going to want to pay attention to. The first one being that in order to get rid of this 4 and make it a 1, kind of, it would have to be times 1/4, but squared, if I square root that, it's 1/2. I know that doesn't make a ton of sense yet, but I think it will once we get going. 1/2 tan theta, which means that dx is 1/2 secant squared theta d theta. All right, so when I plug in, I have the integral from 0 to 1/2. Wait, we're going to leave that off for a second. I'll come back and tell you why. Square root 1 plus 4 times 1/2 tan theta squared times 1/2 secant squared theta d theta. All right, I'm going to show you some steps here that they didn't really show you in the book just because I feel like it's going to help you understand. When I do this, 1 plus 4 times 1/4 when I square it, tan squared theta. My dog is going nuts over here today. Okay, let's go up here. So now my 4 and my 1/4 cancel, and I have the integral of the square root of 1 plus tan squared theta times 1/2 secant squared theta d theta. And we end up with the integral of 1/2 secant to the third theta, because this is secant theta, d theta. Now, what they've done in this example, instead of changing everything back to terms of x, is they have used this to figure out how to change their limits of integration, the 0 and the 1/2, into terms of theta, okay? So here's what we have. If x equals 0, then theta equals 0. So we had the integral from 0 to 1/2. We're still going to have a 0 down here. But if x is 1/2, then theta is pi over 4. And my first question was, where in the world did that come from? But if this is 1/2, right here, x is 1/2, then we do 1/2 equals 1/2 tan theta, divide by 1/2, 1 equals tan theta. And we're working with a right triangle, so we're thinking first quadrant, and that means that theta would have to be pi over 4. That's how we got this, okay? So we're going to do the integral from 0 to pi over 4 of 1/2 secant cubed theta d theta. All right, well, we did secant cubed a couple of times in the section before this. Go back and check it out. Remember that we usually break down our power a little bit, but we end up with 1/2 parentheses 1/2 secant theta tan theta plus natural log absolute value secant theta plus tan theta from 0 to pi over 4. When you plug everything in, when you put a pi over 4 here, and a pi over 4 here, and a pi over 4 here, and a pi over 4 here, pi over 4 everywhere. This dog is killing me. And then you go back and you put in zeros everywhere and you subtract, you end up with 1/4 square root 2 plus ln square root 2 plus 1 as your answer. I feel like I need to go in depth a little bit more on that because I feel like that didn't make as much sense as it should. So let's look again at how we would go from the green to the purple. So if I plug in my pi over 4, well, secant of pi over 4 is square root 2. Tan of pi over 4 is 1. Secant of 0 and tan of 0. So secant is the reciprocal of cosine. At 0, we're at 1, 0, so that's 1. And tan of 0 is 0, because sine over cosine, yeah. All right, 0. All right, so we have 1/2 times 1/2 secant theta is square root 2, tan theta is 1, plus ln absolute value square root of 2 plus 1. That's all for pi over 4. Minus, for 0, we have 1/2, 1/2 secant times tan minus, or plus, sorry, ln of 1 plus 0. Okay. 1/2, nope, let's go ahead and multiply that bad boy. So I'm going to distribute this here and here. So 1/2 is 1/4 square root of 2 over 4 plus ln of absolute value square root of 2 plus 1 over 2. Distribute this one as well. So I have minus 0, that's gone. And then minus ln 1 over 2. Well, ln 1 is also 0, so that's gone. So they pulled the 1/4 out and made theirs square root 2 plus, that should have been 2, ln. How did they have an extra 1/2 that I don't have? Of square root 2 plus 1. So I'm going to have to do a little bit of research on why I have this 2 here and why they do not, but I'll get back to you.